We're going to talk about improper integrals today and the idea of working around asymptotes involving area under a curve. That's what improper is. So we're going to have to use our understanding of limits to be able to deal with these. We're also going to discuss what does it mean for an integral to converge or diverge. These are going to be extremely popular terms for the next several weeks, in fact, for the remainder of the semester. So we want to make sure that we understand this terminology, and then we're going to actually use our knowledge of limits to solve those integrals. So let's go ahead and break this down. We are looking at an integral of 1 over x. I kind of have an idea of what that looks like. It's a rational function from 1 to 100, 1 to 1,000, and 1 to 1,000,000. This is a definite integral, so my answer should be numeric. Now, my calculator is going to do this for me. This is not something that I'm doing by hand. And I went ahead and put this in Desmos for us so we could see the breakdown. So you'll notice, right, I've got three very different values: 4.605, 6.907, 13.815. So I'm going to go ahead and mark those down in my, in my notes here. So I've got 4.605, and obviously the decimal continues, but these are so different that the values are pretty obvious. And then 13.816. So the idea of converging means that I am approaching a very specific value. I am going to a number. And this doesn't appear, obviously, 100 to 1,000,000. I should, from 1 to 1,000,000, if I'm approaching a specific thing, then I should be getting there by the time I get to 1,000,000. But this is growing steadily. So this integral, because it is a horizontal asymptote from 1 to 100, 1 to 1,000, 1 to 1,000,000, it is actually diverging. Okay, so this diverges, and we are not approaching a specific value. That's what diverging means. So now let's take a look at e to the negative x. And that graph does have a horizontal asymptote. I'm going to be getting closer and closer to 0, just like 1 over x did. But am I approaching a certain number? So let's take a look here. Here's my improper integrals evaluated, and then I went ahead and did the 1 to 1,000,000. But 1 to 100 is 0.36787. But so is 1 to 1,000. In fact, all of these decimals are exact. You're talking about 10, 11, 12 decimals being the same, even though I added 900 x values. And then what if I went from 1 to 1,000,000? It's the same thing as well. So this is an example of an improper integral, but that is converging to a specific value. So this is converging. Let's write these values down. So we've got I'm going to keep several extra decimals here. Even though we only work within the thousands, I want to make sure you understand kind of how far this goes. So 0.36787,944, but then this one was also the same thing. So this is converging. And what is it converging to? Well, it's converging to that decimal, 0.36787,944. Right? And it kept going. And in fact, that value is equal to something specific. It's not a random decimal. So we're going to look at that shortly to make sure you understand how to get the exact value instead of having to round this. Now let's talk about what the graphs look like and why one is converging and one is diverging. So 1 over x and e to the negative x, we're going to evaluate looking at these two windows. So I'm going to come back to everything that I have down here. I want to go ahead and look at Desmos. So I'm going to look 0 to 5, negative 1 to 2, so pretty small window there. But then I'm going to zoom in on the y-axis, and then I'm going to make my x really big, and we're going to see how these graphs look different. So let's take a look at the first. So this is, the red is the 1 over x, and the blue is the e to the negative x. So if I'm just looking from negative 1 to 2 on the y-axis, these graphs have a very similar shape, but you can tell that one is getting closer to 0 faster than the other one. The blue is getting much closer to 0 here okay, than the red is, even though their shape is really similar. So now what happens if I look at a much different window? If I change the window, right, the red is still the 1 divided by x, and the blue is still the e to the negative x. You can barely see the blue. You can see the red still has that same general 1 over x shape, but the blue is literally on this axis. You can barely see it because it is so close to 0 that it is literally immeasurable. So that is the difference in these graphs as we go to infinity. So one is converging because it is getting close enough to 0 fast enough. And the other one is diverging because it is not approaching 0 fast enough. It has to do with how fast you approach 0. They're both approaching 0. They're both getting closer to 0, but one is getting closer to 0 much faster than the other. So when I went ahead and drew these graphs ahead of time, I would like for you to sketch these. So I've got a picture here. This is that 1 to 5 kind of scenario, and this is 1 divided by x. So that's the same general shape, and then I can tell that the e to the negative x is going to get closer to the x-axis, but where it really comes into play is when I zoom in and I have a really small y-axis. So this is from 1 to 500, but I've got a really small y-axis here, right? So the highest point is going to be 0.01, and that's the difference in these graphs. So you can have measurable area here where this brown is, where here under the red, that area is not measurable. Okay, it is that close to 0. So this is all very abstract, okay? So the idea of, okay, I'm approaching 0, but I'm approaching 0 fast enough, and that's what it means to converge versus diverging. So I went ahead and wrote a note that the area being accumulated underneath the y equals e to the negative x graph becomes so small so quickly that it soon becomes negligible. It has to do with how fast you're getting to 0. And the area for 1 over x is very small, but it's not small enough to be counted as 0. And that's the difference between converging and diverging improper integrals.